So this will be, today we're going to talk about electron configurations and maybe get a little bit into atomic or periodic trends. This will be the last stuff that you'll see on the exam on Wednesday, because obviously our next class is Tuesday, and that wouldn't really be fair. So yeah, I think. All the exams are cumulative of the whole semester, but it will focus on chapters 4 through 8.
Is it going to be like the same format as the last exam?
Yeah. Any other questions, exam-wise? I wanted to try something. We'll see if I can get it to work. But because I have it all set up for streaming and stuff anyway, would it be helpful if I was online at some point this weekend to like answer questions? Would you be around? When do you plan on doing most of your studying? Sunday at midnight? I'm not going to be up that late. I'm sorry.
No, I'm joking. Sunday, maybe.
But like Sunday? So if we shoot for like a Sunday evening type time, people would be able to be online and ask questions if you need to. What? You can use a phone or something. I'll probably do it on like on either YouTube or Twitch, so that you can send comments and stuff. Yeah. So I'll try to confirm a time. The only thing I'm worried about is my internet at home is really slow because I'm cheap. So like it may not be fast enough to like have a good stream, but we'll try it and see. So we'll shoot for Sunday night, and if it works, maybe we can do like Monday night too, and then we'll have class on Tuesday. All right. Okay, good. So hope your studying is going okay. It's a lot of new stuff, especially Chapter 7 is probably stuff that you really haven't seen before, haven't looked at before. So let's start a little bit just with review from the last couple days and a couple problems with Chapter 7 stuff before we get into the new, Chapter 8 stuff. All right. So let's start with some of the calculations, and we'll review this a little bit more in the second half too when we go downstairs. Okay, so here are 5 orbitals. Which one does not exist, and how do you know that that one does not exist?
6G.
Why 6G?
Well, from what I know, is that it's SPTL.
Okay.
That's 1, 2. I think because it can't fit. NG is just like a fusion breakdown. I think you can't fit that much electrons in just one orbital. So
Okay. So maybe the 6G.
6G is just impossible.
All right. Others, what do you think? Agree? 6G is not possible? Dan? 4S. 4S? Okay, why 4S?
Not sure.
Okay, just looks weird. 2D. 2D? Why 2D?
Because the algorithm values of 0 and values of 1.
Okay.
Subtract 4.
Okay. Yeah, so we have to think about, I like the logic in all of those. Obviously one is right and the other ones aren't, but we'll go through that. But I like the way you're thinking through it. We have to ask ourselves, like, what is it that causes these orbitals? Where do they come from? What are they? And what they are is parameters to this equation, to this wave function. So we have rules about those parameters, right? What are the rules about n? What types of values can n take? What?
0 to
Close.
real.
There's no n equals 0. But so it starts at 1 and goes up from there, right? So n can take values from 1 and so on. Okay. So then we have L. What was the rule for the types of values that L can take? Yeah, it can go 0 to n minus 1. And so n specifies the principal quantum level, the main energy level, and then L gives us the type of orbital. And we said that these numbers, these L numbers, correspond to these letters, S, P, D, F. And in fact, as Yusuf said, those are the orbitals that we generally consider because those are the ones that have electrons in them in the ground state in our set of 118 elements. So does that mean that things that are not in the periodic table do not, that orbitals that are not occupied by electrons in the periodic table also do not exist, or do they still exist, they just don't have electrons in them? Yeah, maybe. So it's a trickier question than that. Because what is an orbital? An orbital doesn't really exist by itself, right? It's describing the probability of an electron. So if an electron is not there, does it still exist? Yeah, but if we gave the electron enough energy, we could jump it into that orbital, and then it would be in that orbital, and it would exist. So generally, the way we think about it is that we say that they do exist even if they're empty. Even though that doesn't necessarily physically mean anything, because an orbital without an electron in it is not really there, but because it's a possible state for an electron to take if it gets enough energy, we're still going to say it's kind of there. So let's look, for instance, at the 6G. So G orbitals are not really a thing that we talk about. They're, and as we'll see when we do electron configurations, in all of the elements we know, there's no element that has an electron in a G orbital in its ground state. But does that mean it can't exist? No. So let's think about what that would actually mean. A 6G orbital would mean n equals 6 and L equals S, P, D, F, G. L equals 4. So that's entirely possible, right? Because that L number is less than n minus 1. In fact, in the 6th quantum level, we would expect to be able to find the possibility of having H orbitals also, right? Which would give us that L equals 5. So that even though that isn't like a physical reality necessarily for what we're going to talk about later, those still can exist, and that still is a valid way of describing the wave function, describing the probability of an electron. So that one is actually real. We can look at these numbers for each of these, and then that's really the best way to decide the answer to the question. So the 1s is n equals 1 and L equals 0. The 2p is n equals 2 and L equals 1. The 4s is n equals 4 and L equals 0. The 2d is n equals 2 and L equals 2. So now looking at those numbers, which one is clearly not possible? Which one violates the rules of which quantum numbers we can use? It's the 2d. Let's move this over a little bit. Or not. Okay. It's the 2d because it's n equals 2 and L equals 2. That is not allowed. In the n equals 2 shell, the highest possible L number has to be 1 because that's n minus 1. And so the 2 shell can only have s and p orbitals, not d orbitals. All right, let's try another one. A little bit different. I think this one is in the homework too. A heat lamp produces 32.8 watts of power at a wavelength of 6.5 micrometers. And we'll talk about watts and what that means. How many photons are emitted per second? All right. We need one more piece of information here. Maybe you know it, maybe you don't, but it's not something you need to know for this class. And that is what a watt is. Power is energy per time. So 1 watt is 1 joule per second. All right. So we want to know, so we got this lamp, a heat lamp, so it's producing in the infrared at 6.5 micrometer wavelength. We know it's producing a certain amount of power. So per second, it's producing 32.8 joules. We want to know how many individual photons are that. I'm thinking of light as little packets of energy called photons. How many photons would that be? So any ideas how we would, what kinds of information we need in a problem like this, where we can start here? Yeah.
Well, using the wavelength, can we find the energy?
Yeah, what are we finding the energy of when we do that? I mean, kind of. So you're talking about this, right?
Yeah.
So what is that energy when we use this equation? What are we finding the energy of? Of a photon. This is the energy of an individual photon. So when we use that equation, we're saying, what is that specific packet of light, that photon with that wavelength, what is the energy of it? And yes, I agree that that is a good place to start. So let's do that. So we'll take Planck's constant and the speed of light. And then we will divide it by the wavelength. Now that's 6.5 micrometers. We need it in meters. So micrometers is 10 to the minus 6th meters. So that would be 6.5 times 10 to the minus 6th meters. Just a little hint, this is a good time to review your metric prefixes if they didn't quite sit in, especially the small ones. So you got meter, and then millimeter is 10 to the minus 3, micrometer is 10 to the minus 6, nanometer is 10 to the minus 9, femtometer is 10 to the minus 12. You don't need to get any smaller than that for chemistry. Okay, so that's the energy of our photon. Oops, calculator. Go ahead and calculate along with me just to check. I get 3.06 times 10 to the minus 20. And that is in joules. Anybody else confirm that? Does that work? Okay. Another thing to do when you're doing these types of calculations with all these big and small numbers kind of together is just take a quick look at your exponents, at your powers of 10, just to make sure your answer makes sense. So I've got 10 to the minus 34 times 10 to the 8th, which is going to be about, what is that, like 10 to the minus 26. And then I'm dividing by 10 to the minus 6, so it's going to take it down to the minus 20. So that looks about right. If that number came out to like positive 20 or 10 to the positive 20, then I'd know like something went wrong somewhere and I should recalculate it. So remember that photons are really small. They have a tiny amount of energy. So that energy of a photon, even if it has a pretty high wavelength, should still generally be pretty small. I'm sorry, even if it has a very small wavelength, it should still be pretty small. All right, so that's our energy of our individual photons. So how do we, yeah? Oh, sorry, the Planck's constant is joules times seconds, not just joules. Yeah, thank you. All right, so how do we use this then? What's our strategy here for the rest of the problem? We know the energy of each photon. How do we figure out the number of photons emitted per second? Yeah, so if we're thinking of light as a collection of photons, then the number of photons is going to be the total energy divided by the energy of each photon, of each piece. So our general strategy is going to be the number of photons is whatever the total energy is divided by the energy of each photon. If you want to think about it in a unit conversion perspective, we could say like the total energy and then times kind of the reciprocal, so like number of photons per energy. But anyway, that works fine. So the total energy we're given in the problem, it's 32.8 watts of power, but the question's asking how many are emitted per second. So to get the energy, not the power, but the energy, we would say 32.8 watts, which is joules per second, times 1 second. That's going to be the total energy in 1 second is 32.8 joules. So then to finish the problem, we take that 32.8 joules and divide by our energy of each photon, 3.06 times 10 to the minus 20 joules per photon. You can imagine this can be a pretty big number. That's our total number of photons. So we took the total energy divided by the energy of each photon. There's several questions like this in the homework. I'm not going to put a bunch of these on the exam, but you might see one. But in general, they're looking at like pulses or collections of energy that is really a collection of photons, and then you want to know what's the energy of each photon and calculate it accordingly. Yeah. Well, did I not do that right? Anybody else? 20, 21? 21? Because 32.8, we can think of that as 3.28 times 10 to the 1. So 10 to the 1 divided by 10 to the minus 20 should be 10 to the 21, I think. So maybe you put 3.28 instead of 32.8 or something like that. Okay. So other questions about this kind of stuff?
So when you multiply the power by 1 second, is that just because it does per second?
Yes. Yeah, because it says per second right here. If that said how many photons are emitted in a minute, then we would have to multiply it by 60. Because the watt gives us per second. Yeah. Anything else? Okay, good questions, everybody. Another thing that you may see in the homework, just to review a little bit from back in chapter 4, because photons are described in very large numbers usually because they're very small, they don't really have size, but they have they have energy, and there's usually a lot of them. We can also describe them in terms of moles. So you may see some problems where they're talking about moles of photons, in which case you can simply convert by the 6.02 times 10 to the 23rd if you need to. Okay, let's talk about the periodic table and how we get that. So you may have noticed that it's kind of an unusual shape. Yes, no? You know where that shape comes from? Why it's kind of spread out in that way? Yeah, well, we're going to find out. I'm not going to tell you right now. But it should become clear relatively soon. Okay. The short answer is electrons. It has to do with electrons and where the electrons go in the atom. And we know now that where the electrons go in the atom are called orbitals. Thank you. Very good. Okay. So let's look at what those electrons are doing in the atom and how we can kind of figure out where they are and which orbitals they're in. So we've talked already about all these different orbitals. And we can kind of make a chart now of orbitals. So we can look at each different n level, and we can say which orbitals are actually in that n level. So we got the n equals 1 level, n equals 2, n equals 3, and n equals 4, and we'll just leave it at that for now. And based on our quantum numbers, we know that, or what do we know that's in the n equals 1 level? What kind of orbitals are in there? S. Anything else? Nothing else, right? Because L can only be 0. So in the n equals 1 level, all we have is an S orbital. How many different S orbitals do we have in the 1 level? How do we figure that out? The answer is there's just one of them. But the reason for that answer comes from that third quantum number, ml. What are the different possible values of ml? They go from plus L to minus L. So if L is 0, then ml also has to be 0. So that tells us that that's the only possible orbital. Let's look what happens when that changes a little bit. So in the n equals 2 level, we can have L equals 0, or we can have L equals 1. So we can have an s orbital, or we can have a p orbital. There's one s orbital, but there's actually 3 p orbitals, because if L equals 1, then ml can be minus 1, 0, or 1. Okay, let's build it up a little bit more. So what do we have in the n equals 3 level? Yep, so we still got S. We still got our 3 p orbitals. But now we're adding d orbitals. And how many of those do we have? Five, right. So L equals 2, which means that ml can be minus 2, minus 1, 0, 1, or 2. So that's 5 total orbitals. All right, and then what about the n equals 4 level? What do we have there? We got our S1 again. We got one s orbital. We got 3 p orbitals. We've got 5 d orbitals, and what do we add? Not quite yet. F. And how many are there? 7. So you start to see a pattern here? Okay. So now we're going to talk about putting electrons in those orbitals. Let's look at just this first orbital, which we call the 1s orbital. And we want to know, what are the possible quantum numbers in this particular orbital. So what are the possible numbers? What's n? N's got to be 1 because it's the 1s orbital. L's got to be 0. ML's got to be 0. And what about MS? Yeah, plus or minus 1/2. So we can have 1/2, and there's like basically 2 sets of possible quantum numbers for an electron in that orbital. It can either be 1, 0, 0 1/2 or 1, 0, 0 minus 1/2. Yeah. You can do it however you want to express it. There's no like official notation for doing this. I just wanted to show that there's 2 possible sets of quantum numbers. All right. So this kind of helps us answer, or using a principle called the Pauli exclusion principle, we can kind of make some conclusions about what's going on with the electrons in the 1s orbital. This is a pretty simple rule, and it just says no 2 electrons in an atom can have the same set of 4 quantum numbers. So every electron has to have in an atom has to have its own unique set of quantum numbers. That doesn't mean that they all have to be different, but they can't be entirely the same. So another way of wording this then is, how many electrons can fit in a 1s orbital? 2, because there's 2 possible sets of quantum numbers that they can have. So the kind of effect of this is that we can only have 2 electrons per orbital. So let's look now. We would expect the exact same situation for every one of the s orbitals in every single shell. Like if we jumped all the way up to the 4s orbital, and we think about the possible quantum numbers for the 4s orbital, it's still n equals 4, that's what changes, but then it's still L equals 0 and ML equals 0, and MS can be plus or minus 1/2. So no matter how high we go in n level, we can still only put 2 electrons in an s orbital, as we can in any other orbital. Okay, let's look what happens when we get to the p's. The p's start to be a little bit different, because if we just talk about the 2p level as a subshell, remember 2p isn't exactly an orbital. That's a set of 3 orbitals. So we call the 2p level a subshell, or a sublevel. The orbitals are actually the 3 different p orbitals that we call px, py, and pz. And remember that even though there's 3, they don't correspond neatly to the quantum numbers. So the ML values are minus 1, 0, and 1, but we can't correspond an ML value directly to like we can't say that the px is ML negative 1. They don't correspond directly like that. So as an exercise, I want you to write that list of 4 quantum numbers, and I want you to write every possibility for the entire 2p subshell. So any electron in a 2p orbital, what could its quantum numbers be, and what are all the different possibilities? So you should have a set of things like this. I'm not going to tell you how many there are. You can maybe figure it out or just start listing them and see what you get. But I will give you a hint, there's more than 2. So what are all the possibilities for that? See if you can write them all out. So how many different sets of numbers are you coming up with, do you think? Around 6? Thereabouts? Let's see if we can find them all. So we know, let's assume that you're right and there are 6. What do they all have in common? The first two numbers are going to be the same, right? Because we're talking about the 2p subshell. So that means that they're all going to start with 2, because n equals 2. And we're talking about the p's, so that means that L is going to be 1 in all of these cases. So where they differ is going to be ML and MS. So if we do it kind of systematically, we can kind of vary 1. So we can say that the minus 1 ML has possible values of 1/2 or minus 1/2. Then 0 has values of plus 1/2 or minus 1/2. Then 1 has MS values of plus 1/2 and minus 1/2. All right, and I think that's all the possibilities. Anybody find anything else? No? Okay, good. Because I don't think there are any. Okay, so how many total electrons can fit in the 2p subshell? 6, right? That's what our rule just said. That if you want to put an electron in an atom, it's got to have at least one different quantum number from any other electron. So if those are all the different possibilities for sets of quantum numbers in the 2p, that means that we can have that means we can have 6 electrons in the 2p subshell. All right, how many electrons can we put in each orbital, though, within the 2p subshell? How many orbitals are there in the 2p subshell? There's 3. Let's group them here. So we've got the ML equals minus 1. That's one orbital. ML equals 0 is one orbital. And ML equals 1 is one orbital. So 3 orbitals in the 2p, 2 electrons in each, 6 electrons total in the 2p. All right. So one thing that is going to change now, in the previous chapter we really only talked about hydrogen. Any idea why that is? What's so special about hydrogen? Okay, so it's small, but what is it about it that makes it... Why do we talk about hydrogen when we talk about electron, when we're first starting to learn about where electrons are? What's special about hydrogen's electrons? Not quite, because we're not really talking about the nucleus, so we don't really care as much about... I mean, it is the lightest, you're right, but we don't really care so much about the nucleus. What do we care about? It only has 1 electron. Yeah. So it turns out that because of this indeterminacy thing that we talked about, if you can't know where 2 electrons are, then you can't really know what their repulsive forces are. So as soon as you add a second electron, all that nice predictability stuff about energy levels and what the electron is doing kind of goes out the window, because we can't really model that very well. And even now, decades, almost 100 years later, more than 100 years later, before some of this stuff came out, we still don't have a true solution for these this electron behavior, because it's so hard to model this repulsion between electrons. So now in this next chapter, we're going to be looking at what happens in multi-electron atoms. So we can make some generalizations and we can think about some general things, but we don't actually have specifics about what the electrons are doing to each other, because we can't exactly know where they are and where they're going. So the first thing that happens in multi-electron atoms is called shielding. I'm going to grab a picture of this from the book. So this is in chapter 8 if you want want to follow along. Oh no, stop. I'm not touching it. There's ghosts in the computer. Okay, that's better. It just takes it a minute to think about or something. All right, so if you think about the nucleus of a lithium atom, it's got a 3+ charge. And it's got 3 electrons. So depending on where those electrons are, the inner electrons will shield the outer electrons from that nuclear charge. So the way that this is modeled here, that cloud, that blue cloud, is meant to be the 1s orbital, which is going to be the closest to the nucleus, with its 2 electrons in it, because we just talked about how there's 2 electrons in the 1s orbital. All right, so you got your 2 electrons in the 1s orbital. Each one has this charge of -1. So the third electron, which is outside that 1s orbital, it's actually a 2s, we would say is shielded from the pole of the nucleus. So the overall charge that outer electron feels is more like +1 than +3, because that full +3 charge is shielded by those other 2 electrons. Does that make sense? So it kind of like goes down by 2. So the further you go out from the nucleus, not only do you have less of a pull just because you're farther away, but you also have these inner electrons shielding that pull from you. So the magnitude of it feels smaller to that electron. So in general, the more or certain types of orbitals experience more shielding than others. So in the hydrogen atom, we only talked about the n levels, and we said, okay, you got your lowest energy close to the nucleus, and then you got your higher energy in that Bohr model. But we know now that's not quite right, because the orbital shapes aren't just shells. They're not just orbits, they're clouds. And so that electron can be anywhere in that cloud. So even like a 2s or a 3s or a 4s orbital can actually penetrate in close to the nucleus. On average, it's not going to be quite that much, though. So let's take a look at comparisons of some orbitals and their radial distributions. Let's grab both of these. Okay, so the graph on the left shows the radial probability, which remember is slightly different from the actual probability distribution, because we know that the electrons can't actually be in the nucleus. So you see the 1s orbital is kind of in purple, and its radial probability is very close to the nucleus. That's in picometers. So its maximum radial probability is right by the nucleus. The 2s orbital, which is in red, has a maximum that's farther out from the nucleus and actually farther than the 2p. But because it also has a little bit in right close where the 2s is, which is called the penetration, the overall radial probability ends up being kind of like the average probability ends up being a little bit closer. So this 2s has a little bit of, if the electron is in that little bump there, it's not shielded anymore by those other electrons. If it's outside, it is shielded. So overall, that 2s is going to feel less shielding than the 2p because the 2p doesn't penetrate in quite as much. If we look at it now in the n equals 3 shell, now we have the 3s, the 3p, and the 3d. Again, it looks like the 3d is closer to the maximum is closer to the nucleus, but because of that extra penetration here by the 3s and the 3p in those lobes that we saw Tuesday, you actually end up having a lower energy situation for the 3s than the 3p or the 3d. Okay, so what does this all mean? This means that depending on the atom, we can figure out exactly what types of orbitals those electrons are going to be in simply by knowing which orbitals are lower energy than others and then putting the electrons in order. So we're going to use a diagram from the book that is helpful but is not exactly correct. And it's right here. And then we'll talk about why it's not exactly correct. So here's where I'm going to make some corrections. It is true that this is a general ordering, and that works okay. It's not really based on energy once you get up near the top. And it only really works when we talk about filling orbitals with electrons. Once the electrons are in there, it's not quite true, which is why I have a little bit of a problem with this diagram. But the fact is that it's helpful, and it will help us get the correct electron configuration, even if physically it's not quite right. So what you do with a diagram like this is you say, okay, we can figure out how many electrons an atom has, and then we can build up the electrons from the bottom up and know where those are. So let's take an example. Pick an atom. What'd you say? Argon? Iron. Okay. Iron's tricky. Let's pick an easier one. Argon. Okay. We'll get to iron and uranium and stuff in a second. But let's first do something like argon. Okay. So how many electrons does a neutral regular argon atom have? 18, right? Same as protons. So what we do is we take this diagram and we start building up our electron counts, counting from 1 to 18. So one way that we do this, and that you'll see kind of in the book, is to draw up arrows and down arrows to make sure that we're accounting for the spin of plus half and minus 1/2, just so we don't accidentally put too many things in the same orbital. So 1, 2, that's our 2 electrons that fit in the 1s orbital. Fit isn't quite right, but that have 3 common quantum numbers and 1 different. Then the next orbital up is our 2s. 2 more electrons go in the 2s. Now we go, what's next? What's next? 2p, right? See that? Next in order? Great. So let's put our electrons in the 2p, but now we have a choice. We can fill the orbitals from left to right, just 1, 2, 3, 4, 5, 6. Or we can actually fill them like 1, 2, 3, and then 4, 5, 6, pairing second, because all those p orbitals are at the same energy. And we actually have a name for that. When orbitals are at the same energy, we call them degenerate. And do you think that it is stabilizing, or do you think that it is destabilizing to have 2 electrons in the same orbital? Are they going to help each other out and be happier together, or are they going to, would they prefer to be apart? What's your guess? Why? You're right. Yeah, because electrons are negatively charged, they repel each other. So if the orbitals, as we know, are a particular spatial thing, 2 electrons would rather not be in that same space if they can avoid it, because they're going to repel each other. So because of that, we're going to fill the orbitals, minimizing the amount of electron pairing that we have. So that means when we count 5, 6, 7, 8, 9, 10 for our next electrons, we're going to count 5, 6, 7, and then pair them up. 8, 9, 10. Yeah, that works? Okay, so are we done? We're good? We got all the electrons for argon? Not yet. We got 10. So what comes next? Where do we put the next ones? The 3s. So we'll put 2 there. And then where? 3p. And we're going to do that same technique. Now for argon, this ends up not mattering because they all get paired up anyway. But as we'll see in a little bit, atoms where they don't get paired up end up having some different properties. So that idea that they are filled separately is actually experimentally verifiable, that they're not paired up until the end. Okay, so now we got 18 electrons in there, right? And we're good. So all that's left to do is to write what we call an electron configuration. Now in an electron configuration, we don't really care which specific orbitals the electrons are in, because we often don't know. As we get into compounds and stuff, sometimes we'll know, but we're just going to talk about the subshells and the electrons in those subshells. So an electron configuration looks like this. You write the orbital, like 1s, and then you use a superscript to write how many electrons are in that orbital. So there are in that subshell. So there are 2 electrons in the 1s subshell. So we would write 1s2. And then directly next to it, we keep going just the way that we built it up. So now we've got 2s2. And then when we get to the p, we're going to include all the electrons in the subshell. So we're going to say 2p6. Three s2, 3p6. So that's our entire electron configuration for argon, which describes exactly all of the stuff that we just did with our electron building up. Okay. So now think about how that configuration now compares to the layout of the periodic table. Look at period 1, which is our first row. How many atoms are in there? 2. What types of shells are they filling their putting their electrons in? S, the 1s specifically, right? So the first row, hydrogen, helium. Hydrogen's going to have 1 electron in the 1s. Helium has 2 electrons in the 1s. Then we jump down a row. Where do the electrons go first when we get to lithium? Which shell in lithium is going to be, again, it's the 1s, but then the 2s is going to be the outer one, right? Beryllium fills that 2s. And then we make this big jump. Where are we going when we get to boron? The 2p. How many electrons fit in the 2p? How many atoms are kind of over on the right side in that chunk? 6, right? And in fact, we refer to the periodic table often based on these subshells. So we talk about the first 2 columns as the S block elements. We talk about the right side, those 6 columns on the right, as the P block elements. What do you think is going to happen in the middle? The D's. What do you think happens in that row on the very bottom? The F's, yeah. So let's look at how that works and how we go about building those electron configurations. Oh, so I should also mention unpaired electrons in the electron diagram or configuration lead to a physical property called paramagnetism. Paramagnetism, or things that are paramagnetic, are attracted to a magnetic field. So you can actually test if something has unpaired electrons or not by seeing if it's attracted to a magnetic field. And as we'll see in a couple chapters, actually, sometimes that makes us question our assumptions of which things that we have paired up based on these kinds of rules. The opposite is diamagnetism. If there are no unpaired electrons, we would expect that to be diamagnetic, which means that it excludes magnetic fields, it's repelled by magnetic fields. So that's just a little bit of an aside. Okay. So one thing that, looking at the periodic table like that, we should be able to write these electron configurations without doing that every single time. So take a look at argon. We just did argon, and we said that its electron configuration was 1s2, 2s2, 2p6, 3s2, 3p6. Another way of thinking about that is looking at the periodic table and saying, okay, 1s2 is top row, 2s2 is 3 and 4, then 2p6, because there's 6 over there, then 3s2, then 3p6. So what do you think is the configuration? Let's see if we can write an electron configuration for oxygen without actually like building everything up from the bottom. Based on its position in the periodic table, what is the electron configuration for oxygen? 1s2 because it's in the below the first row. Then what? 2s2 and careful. We're still in the second row. So we're going to go 2p4. Now that should add up to 8 because oxygen has 8 electrons. Does it? Yes. But we didn't actually have to count up every single electron to do that. We just had to recognize it's the fourth one in the p block, and therefore it's got to be a p4 element. Also, it's in the second row, so it's got to be a 2p4. Okay, so that's good. What if it gets big? So like that argon configuration wasn't too bad, but what if we're writing like, somebody said uranium, right? One of these giant elements, that electron configuration is going to be really, really big. So there's a shorthand that we use where we say, okay, everything above is assumed, and we're only going to write kind of like the special new ones, and we're going to ultimately have kind of a term for that. If we go back up, or if we look at oxygen here, so we could call that 1s2, 2s2, 2p4. We could also say, okay, we're going to start with helium, the noble gas on the first row, because we know it's got that full, and then we're going to count up from there. So another way of writing electron configurations is to start with the nearest lower noble gas, and then just write the rest of it. All right, so for instance, if we looked at phosphorus, we could again go 1s2, 2s2, 2p6, whatever. Or we could say, okay, phosphorus is in the third row, and the nearest lower noble gas is neon. So another way we can write phosphorus's electron configuration is neon, and then the 3s2 and the 3p3. Another reason for doing this is that these electrons are more important chemically than these electrons. So we actually give them separate names. Anybody know what those names are? You've probably heard them before. You know what those outer electrons are called? Yeah, these are the valence electrons. And the other ones, everything else in the whole atom, is called core electrons. The reason why do you think the valence electrons are the most important? Yeah. They are in the outer shell. So these are going to be, specifically the valence electrons are in the highest n level. And they include all subshells in that highest n level. So even though we see in the chart that the p orbitals are a little bit higher than the s orbitals in energy, the they're all considered a part of the valence level because that difference is not quite as big as the difference between those n levels. All right, so those are the highest level ones, and the core is everything else. So what's important about those? Why do we care that those are the outermost ones? Those are the ones that interact with other things. Why? They're not as stable. Why? Okay, so what's happening if they're farther from the nucleus? They're shielded from the nucleus. So it's actually more than just the distance. It's the shielding of those inner electrons. If we go back up to that picture that we saw earlier, right? As we go to higher n levels, those electrons are more shielded from the nuclear charge, that pull of the nucleus, than the core electrons. And in fact, this is so much the case that, as we'll see later in the chapter, that it becomes nearly impossible to do anything chemically or to interact at all with core electrons. So we end up, for the rest of the semester, basically ignoring the core electrons and really only caring about those valence electrons. All right, so let's look at some kind of unusual things that happen in electron configurations that we have to be aware of in order to write correct ones. So we'll get another energy diagram here. Okay, what do you notice happening as the levels go up? As like the n levels go up, what's happening to the energies of the orbitals? They're kind of like getting closer together. See that? Which is predicted from our calculations of the energy levels of the hydrogen atom, because we know that as we get to higher n levels, the distance in energy between the levels gets smaller. So, what ends up happening is the distance between the n levels ends up kind of being a little bit, or being in conflict with the difference between the different subshells. So if we get up, once we get up to the 3D, you'll notice that the 4s is actually listed as lower than the 3D. Now, I should make clear that is not actually accurate. It is not true. The 3D orbitals are indeed lower energy than the 4s. But when we're adding electrons to an atom, because those are so close to each other, and because there's other things going on inside the atom, it ends up kind of getting a little bit confused. So when we write electron configurations of neutral atoms, the s electrons of the shell of the next shell end up being preferentially occupied by electrons to the d orbitals of the lower shell. So when we go with iron, let's take that example now. Iron has 26 electrons, so we're going to fill everything up that we did for argon, which is those 18. Whoops, let's do this the right way. And remember that we often want to just abbreviate that as argon, so we don't have to write that whole thing out. Okay, so now past argon, we've got the potassium, calcium, and then scandium, titanium, vanadium, chromium, manganese, and then we get to iron. So that looks like this. We're going to fill the 4s first, and that's the s block, that's potassium and calcium. And then we add those 6 electrons to the d to get up to 26. And using our principles that we've learned, we know that when we fill the d orbitals with 6 electrons, it's going to look like that. All right, so that's something that gets a little bit tricky. But if you forget that ordering, you can actually use the periodic table to help you. If you remember that you have to fill the s block first, then you know that when you get to the fourth row here, you've got to go 4s2 for potassium and calcium, and then the Ds. So let's look at how that happens when we get to the Fs, just from the periodic table. Because it gets otherwise, and then we can check ourselves. Actually, no, there is no F up there, so we can't check ourselves for that. So we get to the Fs when we get down to the sixth row. We would first fill our 6s. Then we would jump down here and start filling the 4f. We have 14 electrons in the 4f. Then we go back over to here, and so what are we then filling here after we do the 4f? 5d, yeah. So we're gonna the D block here is always one level lower than whatever the S is that you just filled, whatever the period number is. So we got the 6s, the 5d, and the 4f for those really heavy elements. All right. And you'll get to practice some of this downstairs and then also in your homework. All right, so that's nice, but now let's talk about where it gets weird. Not that that wasn't weird enough. But because it's chemistry and because we're dealing with real things, there's always exceptions. There's always things that don't quite follow the rules as nicely as you would like them to. So there's a nice table in the book of all the, basically the valence electron configurations throughout the periodic table. If you look at that for reference, you'll realize that if you actually wanted to know the electron configuration of every single element, you would really have to just memorize a bunch of stuff. And we don't want to do that. So these rules that we're coming up with work mostly. But if we look at just kind of a zoomed in picture of the inner transition metals there, so this is from 21 to 30, so just the transition metals in the D block there. You'll notice that the first row mostly works the way we would expect it to. So we fill up the 4s, and then we start filling up the 3d. But there are two spots where it doesn't quite go as planned. And those are here, chromium and copper. So chromium, if you'll notice, is 4s1 3d5 instead of our expected configuration of 4s2 3d4. Any idea why that is? Why might it do that? I'll give you a hint. Okay, so here's what 4s2 3d4 would look like. Here's what 4s1 3d5 looks like. Yeah, in the bottom case, we've got no paired electrons. So when we talk about chromium, we talk about how there's this pairing energy that costs energy to pair electrons together in the same orbital. So we expect in that case that the electrons would rather kind of spread out. This also is some evidence against the ordering order, or the filling order, because really what's happening here is the 3D are filling first, then the 4s can go up there because it doesn't want to get paired up. So that pairing accounts for chromium. It doesn't account for copper. Any guesses what's going on there? Why does copper also take one of the electrons from the 4s and keep it in the 3d instead of putting it into the 4s? Well, I mean, that's what we're saying, but why then would it come down? Oh, I'm sorry, you said the 4s is higher at that point? Yeah, kind of. there's another energy associated with filling an entire orbital. So the fact that if one electron comes down, then the d shell is totally full, that lends a special stability to that shell. And so in positions in the periodic table where a shell can fill like that and the energies aren't that different, that will often happen. So you should know these two common exceptions and the reasons behind them. But if you look down now to the second row, you'll see it gets even weirder. And there are now 6 out of the 10 that are not quite as expected. You've got niobium at 5s144, molybdenum at 5s145, and so on. And that has to do with various chemical effects, but basically that those differences in energy become such that the pairing energy becomes more significant. There's also coupling between some of the electrons in the orbitals and all kinds of stuff going on. So you're not expected to know all these configurations throughout the periodic table, but just know that as we get lower in the periodic table, some of these predictable rules kind of break down. So we can't always get that. All right. So the last thing we're going to look at with electron configurations is ions. What happens when we add or remove electrons to these elements? What happens to their electron configurations? Right, so some of it is very straightforward and obvious. Like, for instance, if we look at sodium, whose electron configuration is neon 3s1, and we want to look at a sodium ion, what would you expect would be the electron configuration of a sodium ion? What? Just neon, yeah. So we remove that 3s1 electron, and we have neon. Looking at that also has a really powerful explanatory power, as the book puts it, that because we see that one lone electron way out, shielded from the nucleus, we would expect or be able to predict that we would lose that electron, that it would not cost too much energy to lose that electron. And in fact, that's what happens. And we know that the most common ion of sodium is +1. So all the stuff we learned in chapter 3 with common ions being in particular places in the periodic table, now we actually have a theoretical basis for that. We can look at the electron configuration and we can say, yeah, these are the common ions. So that's simple. It also works well if we talk about negative ions. So fluorine at 2s2, 2p5. If we add an electron, we have 2s2, 2p6, which is the neon configuration. So we're starting to see this pattern of like atoms getting to noble gas configuration. The only thing that is a little different and is worth remembering with regard to forming ions here is when we have things like our transition metals. So if we go back to iron, we're going to write our electron configuration like this for our neutral atom. But if we then look at a couple different ions of iron, there are 2 common ions of iron, iron +2 and iron +3, iron 2 and iron 3. We have to be a little bit careful to take those ions or take those electrons out of the actual highest level, the least shielded electrons, which are the 4s2. Okay, so the 2+ grabs those 4s electrons, not the 3ds, even though we wrote them last, even though we filled them last. So the electron configuration of iron 2+ is argon 3d6, not 4s2 3d4. outermost or least shielded electron. And that's why I don't like that previous diagram that we used, because the diagram makes it look like the 3D should be higher in energy, and if that were actually true, then those should be removed first. But that's not actually true. The 4s are still higher in energy, but because of some complicated effects inside the atom, basically the extra 3D electrons get kind of pushed up to the 4s temporarily in the neutral atom. When they're ionized, we get kind of the more expected behavior, which is the outer shell electrons are removed. And then if we were removing more electrons than that, we simply take them as expected. So the 3+ ion of iron, we would expect to remove those, not just another d electron, because that's what's left. So for that reason, we also don't necessarily talk the same way about valence and core electrons when we talk about transition metals and the lanthanides and actinides in the bottom. It's not as simple as it is with the S block and the P block elements, where we talk about like the octet rule and wanting to fill or empty the shells. It's not quite so simple in the middle of the periodic table. So when you do the homework, for instance, they generally won't ask about how many valence electrons a transition metal will have. All right, questions about any of that stuff? Okay, I will see you downstairs in about 15 minutes, and we will practice all of this stuff so we are ready for the exam.